Alright, so this is lecture 1 for MS 110. This is going to be chapter 2. We're in chapter 2, covering the 4 sections in chapter 2, which is called set theory. And this is going to be the set notation section. Okay, a few things before I get going. I suggest keeping the notes outline that I have in Canvas. In the modules tab, you should see it right around where you found this video. I would just keep that open while you're watching the video. It's going to be helpful, at least to me. Those note outlines are actually what I would use in a real person, in an in-person class. I would have that on a little clipboard, and that's what I would actually use as an instructor to keep myself, on track. So you may see some notes to myself in those, in that outline of those notes, but it can be helpful for you too. Feel free to print them off and have them off to the side while you're watching these videos. And you'll see that all the dates are incorrect on all the lectures because I built them last semester. Whatever, just ignore that. Minor detail. Alright, so introduction for this section, and really for this chapter in general. Why do we learn set theory? Well, set theory is a huge field of mathematics, but the scratching of the surface that we're going to do in this course, I would say, is useful in the sense that it's going to teach you, it's going to give you new tools for organization, right? And organization skills are useful outside of mathematics, clearly, just in everyday life. Just being a human being, it's helpful to be able to have good organization skills. Okay. So let's start off with kind of a general overview about what this is going to be about. We're going to talk about a bunch of definitions. We're going to talk about roster notation of a set versus set builder notation. These are kind of be the big ideas here. Roster notation versus set notation, or set builder notation. Equal versus equivalent. Those are two different things. Two sets can be equal. It's not the same thing as two sets being equivalent, necessarily. We're going to talk about what a cardinal number is for a set. Cardinal number. We're going to talk about, let's see, I'm scrolling through some special sets called the empty set and the universal set. And we're going to talk about the complement of a set. I suppose I could say of a set up here as well. These are going to be the main ideas in this section. If you watch this video and with the examples and everything that I do, you feel confident about knowing the difference between these two and what each of these definitions mean, and you can replicate them in the homework problems, these ideas in the homework problems, then you are good to go. So let's get started at the beginning with the definition of a set and some symbols that we'll need to know. Alright. So, since we have the notes already typed up, I'm not going to write every definition down. So, we've got a set, and I'm reading from the notes right now, is a collection of objects made up of specified elements or members, and the notation for elements of a set is that little symbol. So a set, I'll say something different here, can consist of can consist of numbers, objects, letters, any number of things. Any number of things. You can have a set of any number of things. Sets can consist of. Okay. Usually, we denote sets with capital letters. I'm going to say something real quick, in case you're used to a traditional math course like algebra and stuff like that. We're not going to be... This first chapter is not very math heavy. In fact, the second chapter isn't very math heavy necessarily, not algebra heavy. So we're not going to be doing a lot of work with numbers, but more like ideas, like definitions and concepts. We'll use numbers in these example problems, but that won't be the focus. We're not doing a lot of algebra in this class. Okay, so usually we denote sets with capital letters. Some of my favorites are capital A, B, and C, and then for whatever reason, X and Y, and I like to write my capital X and Y with a horizontal line at the top and bottom. And elements of the set, so if it's a set of names of people, one element would be one name. So elements of the set are denoted, if we're just talking about an element in general of a set, we denoted with lowercase letters. And we use the symbol, it's like a C with a line in it, to say an element is in a set. So we could say x, little x, lowercase x, is in A. This is literally read as the element x is in the set A. And maybe less technically, we could just say x is in A. This would be the completely correct way of saying it. The element x is in the set A. But if you already know from the context of the problem that this is an element and this is a set, then you could just say x is in A. So, alright. Okay, let's talk about roster notation. Let's actually look at some sets, because we haven't looked at any sets yet. Roster notation, or roster method, you can call it either. Using the roster method is how you would say it, and the notation itself is called roster notation. Is a way, so from the notes, roster notation is a way to describe a set by listing all of the elements in the set. So roster notation simply means listing each element out. Listing each element. Doesn't get much more simpler than that. However, there are some notations that we should talk about. We use curly brackets to start and close and end a set, and use commas to separate elements. Alright, so let's do some examples, or show some examples of roster notation. So some examples would be the set A, and I'll say is equal to, so now I'm about to tell you what's in the set of A, or what the set of A is. A equals, and then since it's a set, I'm going to start with a curly bracket, and I'll say maybe the numbers 1 and 2. There's one example, and then I close with the other curly bracket there. I could say B is equal to the set 2, 1. I could say X is equal to the set of letters A, B, C, D, separating each one with commas. And Y is the set, maybe some word A, B, C, D. And I'm saying word there like in quotes because obviously that doesn't make a word, but the point is that's one element. These are 4 distinct elements in X, A, B, C, and D. You know they're 4 distinct elements because they're separated by commas. This is one single element. Different. Okay. So there's some examples of roster notation. Now, let's talk about equal sets. Two sets are, from the notes here I'm reading, 2 sets are said to be equal if they contain exactly the same elements. Okay. Okay. 2 sets are equal if they, I'm writing this down because I want to have it down to compare to the definition of equivalent later. 2 sets are equal if they have exactly the same elements. Whoops, exactly the same elements. So, for example, here's a question. In this problem up here, or in this, these examples here, is A equal to B? Think about that. Do they have exactly the same elements? Well, A has 1 and 2, and B has 2 and 1. Those are the same elements. They're in a different order, but they are the same elements. So yes, yes, because they have exactly the same elements. The order does not matter. To emphasize that, let's say I'll make up 2 more sets. C is equal to 2 names. Let's say John and Jeff, and let's do one more name, Mary. And D is equal to Mary, John, Jeff. I could say C is equal to D. C is equal to D. So they have different names, C and D, and they're in a different order, but they have exactly the same elements. They have exactly the same elements. So C is equal to D. Okay, now what about back here in this previous example with X and Y? Is X equal to Y from the previous example? No. They have different elements. Because X has the elements A, B, C, D, 4 distinct elements. Y has the elements, Y has the element, whatever this is, A, B, C, D, right? It's one element. It's one element. This one has 4 different elements, and this is one element. So there's no way they have the same elements. Okay. Alright. So that is the definition of equal. Now, let's see. Okay, so let's look at the cardinal number of a set now. Cardinal number of a set. So from the notes we have that the cardinal number of a set is the number of elements contained in the set, in a finite set, so we're not talking about infinite sets here. And you could also call it the cardinality of the set. And we denote it by two vertical bars. They kind of look like absolute value symbols. So we say this is read as the cardinal number of A, or the cardinality of A. And all this means, all it means is how many elements are in the set. So if I take the example with x and y from a second ago, so example of cardinal number, I could say, let me rewrite the sets. X is the set of A, B, C, and D, and Y is the set, single element, A, B, C, D. Then I could say the cardinal number of X is 4, because there are 4 elements in the set X, and the cardinal number of Y is 1, because there is 1 element in the set Y. And again, there's only 1 element here because we don't see any commas separating these letters. This is 1 element stuck together. A, B, C, D all stuck together, and that's 1 element. Say I've got the set A equal to 1, 2, 3, and then maybe it has these ellipses, and then it goes off to 50. This means that there is some pattern established, and that the numbers continue to follow that pattern all the way up to 50. So this is just counting 1, 2, 3, 4, 5, 6, 7, etc. all the way up to 50. That's what these ellipses mean. So I could say that the cardinal number of A is 50 because there are 50 elements. I don't have them all explicitly written here, but it's understood that this pattern continues and that there are 50 elements. Or I could say the set B is A, B, C, dot dot dot, or whoops, dot dot dot, only supposed to be 3 dots, and then maybe Y and Z at the end. Pretty clear here that this is the alphabet, the English alphabet, right? A, B, C, D, E. So using the ellipses here to denote the rest of the letters, it's just a lazy way of not writing the rest of the letters. If you establish the pattern here nicely, usually with at least 3 elements, if the pattern is understood here, then you can just use these dots to denote the rest of the elements in between. So the cardinality of B would be 26, because there are 26 English alphabet letters, A through Z. There are 26. Good. That is the cardinal number. I have another example listed here in the notes that says, use the roster method to represent S, which is the set of states in the United States that begin with the letter M. Then find the cardinal number of S. Okay, let's do that. So here's how I'm going to do this. I'm going to say example 1 from notes. Okay, so we want to use the roster method to represent S, which is going to, so the roster method means I'm actually going to list these things out, and I want to represent the set of states in the U.S. that begin with the letter M. So let's see here, we've got Maine, we've got Minnesota. Now, I can't use ellipses here because there's not a pattern to this, right? Yes, it's the states that begin with M, but there's going to be so few of them that it won't be that bad to list them all out. And really, this isn't where ellipses would be necessary or appropriate, because you would only use those ellipses if you've established some kind of pattern that is understood, that is implied. Okay. Maine, Minnesota, Michigan, Mississippi. Let's see, Montana. I feel like there's 7. I'm missing one. Or, no, I'm missing 2. Let's see, it's probably driving you guys crazy because you're probably thinking of it. Minnesota, Michigan, Mississippi, Montana. Oh, isn't there another one up north? Let's see. Oh yeah, I'm missing 2. Maryland and Massachusetts. Maryland. Sorry about that. Massachusetts. Massachusetts. 2 T's. There we go. Okay. So the instructions said to list it in roster notation. List this set S, which is the set of all states that begin with the letter M, in roster notation. Done. And to find the cardinality of S, or the cardinal number of S, or the number of elements in the set S, those all mean the same thing, and that's going to be 7. Right, 1, 2, 3, 4, 5, 6, 7, because there are 7 elements. Cool. Alright, let's talk about equivalent sets. This is an even easier definition than equal. 2 sets are equivalent if they have the same number of elements. And we denote that by, so we use the equal sign for equality, for 2 sets being equal, we use the equal sign, which makes sense. We are talking about a different kind of equivalence here. We call it equivalent, and so we need a new symbol. We're going to use this symbol. That's a period there, so that symbol there. That symbol. It's on your keyboard. It's called a tilde. Tilde. I think I'm saying that right. Tilde. Okay. So if 2 sets are equivalent, we would write this symbol in between them. So for example, let C equal the set 1, 2, 3. Let D equal the set A, B, C. 2 sets are equivalent if they have the same number of elements. Well, this has 3 elements, this has 3 elements, so C is equivalent to D. C is equivalent to D. Doesn't matter what the elements are, just means that the elements, that there are the same number of elements. So C is equivalent to D. Is C equal to D? No. C is not equal to D. Because for 2 sets to be equal, they have to have exactly the same elements. Okay, so C and D are equivalent but not equal. C and D are equivalent but not equal. And if I want to say not equal, I can use that, put a slash through it. If I wanted to say not equivalent, I could put a slash through that symbol. Okay. Let's do some more examples. Let's actually do this example that I see in the notes here concerning equivalence versus equality. Example 2 from the notes. from the notes says, determine if the given pairs of sets are equal, equivalent, or neither. So part A says the set capital A is equal to, and then we have, what, 5 topics, I guess we could say classes actually. Music, health, art, biology, and history. And then set B is 5 names: Tim, Gloria, Alan, Warren, and Karen. Okay. A is not equal to B because they're different. But A is equivalent to B. So it's just like the C and D I just gave as an example a second ago. They're not equal, but they are equivalent. What about part B? X is the set of numbers 2, 4, 6, 8, 10, 12. So even numbers between 2 and 12. And Y is the set 12, 10, 8, 6, 4, 2. Even numbers between 2 and 12 there as well. They're just in a different order. So, since order doesn't matter, X is equal to Y, and X is equivalent to Y. Right, if they're equal, then they have to be equivalent. Right, because if they're equal, that means they have exactly the same elements. If they have exactly the same elements, then surely they have the same number of elements, right? Okay, but if just because two sets have the same number of elements doesn't mean that they're exactly the same elements. So if two sets are equal, they are inherently equivalent. If two sets are not equal, they may or may not be equivalent. Let me add an example here of that case where, so these two are coming straight from the notes. I didn't even write A, B, and X, Y down because they're listed there in the notes. But I'm going to do a new example here. I'll say with, I'm going to pick some new letters. How about P and Q? Let's let capital P be the set 1, 2, 3, 4. And Q be the set 1, 2, 3. Alright. Is P equal to Q? No. Why? Because they do not have exactly the same elements. P has everything that Q has, right? Q's only got 1, 2, 3, and P's got 1, 2, 3. But P has this extra element, the 4, that Q does not have. So they do not have exactly the same elements. In fact, also, P is not equivalent to Q because they don't have the same number of elements. Okay, so these are the three possibilities that you can have. Not equal, equivalent, equal and equivalent, not equal, not equivalent. You can never have equal but not equivalent, because that wouldn't make sense. Equal is a stronger condition. Alright, let's move on to set builder notation. Oops. I'll leave that about there. Okay, set builder notation from the notes says, set builder notation is used to describe a set when the members all share certain properties. Okay, and then I've got some notes to myself there. Okay, so set builder notation. Let me give you some examples. Oops. Here is a set. X is equal to 2, 4, let's see, yeah, I'll pick that same set from a second ago, 10 and 12. This is in roster notation, right? This is all we know so far. Okay, so I'm going to take a set that's in roster notation, and I'm going to put it in set builder notation. This is one of the skills that you'll definitely need, going from roster to set builder notation. Here's what I can do. I will say X is the set of all the elements. Let's see, one second. Okay, sorry about that. Okay, X is the set of all elements X, so I just name arbitrary elements of X here with a little x. Why not? Keep the letters the same, just for organization's sake. Such that, so this bar is a new symbol it's a lone bar, and it means such that x is an even whole number and so it's an even whole number, and now I have some options here. I need to cut it off, right? Because the whole numbers, if you recall what the whole numbers are, that's 1, 2, or 0, 1, 2, 3, 4, 5, 6, 7, 8, etc. So I need a way to cut those off. I don't want to have 0 in there. 0 is an even number, so I need to cut out 0, and I need to cut out everything past 12. So, I didn't give myself enough room here to do this. I'm going to use an inequality. I'm going to say that x is an even whole number and x is between 0 and 12, not including 0, but including 12. So I dealt with you got to recall what these inequality symbols do. This means that 12 is included because it has the or equal to sign there. This means that 0 is not included. Now you may say, what about the number 1, right? Because 1 is surely included here, but I excluded 1 back here when I said x is an even number. Okay, so this is set builder notation is identifying some kind of pattern that's happening within the roster notation and writing it in a more concise statement. Well, okay, I suppose this isn't really concise because this is much larger than that, but we'll have better examples. It's a nice way to talk about infinite sets, too. Okay, so let's do more examples. We'll do more examples here. Let's let y equal 1, 3, 5, 7, up to 99. Okay, so here's another set written in roster notation. Now if I want to write it in set builder notation, I start with my set bracket. I write a lowercase y just to represent arbitrary elements of this set, or just some placeholder element. I say such that, so y is an element y is in this set. Sorry, this is how you read it. The set of all y such that, and then I'll say y is an odd whole number. And what should I say here? Y is an odd whole number, and y is less than 100. How about that? So we've got options here. You could say y is less than or equal to 99. You could say that. Or y is less than 100. Or you could even say y is less than 101. That would be getting a little risky. That's getting kind of close to accidentally including 101. But you could do that. So I've got y is an odd whole number, and y is less than 100. I don't need to have a lower bound on this y because the lowest whole number is 0, but 0 is even, so I've already excluded that out by calling it odd whole numbers, by calling y odd whole numbers. So let me break this down a little bit more, and we'll do some of these examples from the notes. A equals, okay, this is going to be set builder notation. This is a element placeholder. Usually it's a lowercase version. It doesn't have to be. Lowercase version of set. So I'll use little a here. Then this bar is read as such that. So now we're about to say A is in this set, these little a's are in this set, such that only if they act this way, and whatever is in here is going to be the description of elements in the set. And it does not have to be numbers. The numbers, they're just nice examples. That's why we use them a lot. But it doesn't have to be numbers. In fact, if you recall from example 1 from the notes, S is the set of all states that start with an M. Remember that. We can write that S as, so I'm calling back to that S from earlier. S is equal to, maybe instead of a little s here, I'll use M for the states, the states that start with M, and I'll say such that M is, and I need to be careful here, I need to say the name of a U.S. state that starts with the letter M. And I'll say capital M because they all start with capital M's. So this would be read as S is the set of all elements M such that, with the conditions that, M is the name of a U.S. state that starts with the letter M. So it's just a description of the stuff that's in the set. Let's look at these examples. This is the first thing that really takes some practice and getting used to. Equivalence versus equality, it's a little weird, but if you just work those definitions a bit, it's not too bad. But this set builder notation gets a little tricky. Oh, let's see. Real quick, before we need to go off on a small tangent before we really get going. We need to talk about sets of numbers, sets of real numbers. So the real numbers are divided up into different sets, whole numbers, integers, rational numbers, and irrational numbers. W will represent the set of whole numbers. W is equal to, a set of whole numbers, 0, 1, 2, 3, 4, 5, etc., off to infinity. Off to infinity, that's 0, and they're all whole numbers, no fractional stuff. Capital Z, capital boldface Z, and I'm doing bold just by making 2 lines here, will represent the set of integers. Why is it a Z? I've got no idea. I don't know why we picked Z. Z is an infinite set in both directions because it includes the negative whole numbers as well. So this is where we get, now that's a curly bracket, that kind of looks like a 3, that's supposed to be a curly bracket. There we go. So all the negative whole numbers, negative 1,000,000, negative 4, negative 45, all the way down to 0, and then all the whole numbers. So the whole numbers are inside of the integers, right there. There they are. All right. And then, let's see, do we need to talk about rational numbers? No, but we should talk about natural numbers. Kind of skipped over that. So that's a capital N with 2 lines there. N will represent the set of natural numbers. N is equal to, capital N is equal to, etc. 1, 2, 3, 4, etc. So it's almost exactly like the whole number set, except the whole numbers have 0, n does not. The natural numbers do not. So we've got whole numbers, integers, natural numbers. You need to know these, because we will use these for examples. Okay, now let's look at example 3 that says, use set builder notation to represent each set. I need this to skip up a bit. There we go. Okay, example 3 from the notes. Use set builder notation to represent each set. We've got part A is y, which we're calling the set of all even integers. Okay. The set of all even integers. Okay, here's how we would do this. Y is going to be equal to the set of all y, set of all elements y, such that, now, we could get a little creative here. There are multiple ways of doing this. I could say y is an element of, remember that symbol, that means is in or is an element of the set z, which is the integers. So right now, so far, I've got y is equal to the set of all elements y, such that, or with the conditions that, y is in the set of integers, so I'm like halfway there, because I'm in the integers. And how do I make y even here? How do I make y even? Well, let's just do this. Let's just call it even. Sure, why not? There are other ways of doing it. In fact, is this from the text? Yeah, they do it another way. They say this. So this surely seems like a fairly straightforward way of doing it to me. But they say the set of all y, and they're using x instead of y for whatever reason in the text. I'm reading the text now. In example 3 in the text. It says the set of all y such that, or sorry, the set of all 2y such that y is in the integers. Now, how does that work? Well, this works because every integer, if you multiply it by 2, is going to become even, right? That's how even numbers can be built, is multiplying any number by 2. Like 1 times 2 becomes 2. 3 times 2 becomes 6. 2 times 2 becomes 4. Every product, every time you multiply something by 2, it becomes even. That's the definition of even. It means that that 2 goes into it. So this is another way. This is a more slick way of writing the set of all even integers. Okay, but this is totally fine. And I think they even give another way of doing it there, but that's fine. Let's move on to part B. Part B says x such that, or x is the set of all odd integers greater than 3 and less than 10. Let me write that down. All odd integers greater than 3 and less than 10. Okay. So x is the set of all odd integers greater than 3 and less than 10. I'll say x is equal to, let me just start with my set builder notation. I know I need the little x and I need the bar, so the set of all elements x such that, now I need to build this set. So I need x to be odd, I need it to be in the integers, and I need it to be within these bounds. So I'm going to start with the most vague condition, which is that x is an integer. I need to know it's a number first, and what kind of number, right? So I need to know that first. X is an integer, and x is odd, and See, I'm getting slowly more specific. Start with the most general thing first. X is an integer. Okay. What kind of integer? Well, it's odd. Okay. Is there any other details? Is it bounded? Is it all of the odd integers? Well, no. It's between 3 and 10. X is greater than 3 and less than 10. So this literally means when x is greater than 3 and less than 10, that means x is between 3 and 10. And the nice thing is when you write that as an inequality, literally the x is between a 3 and a 10, right? So x is between 3 and 10. And we're using the greater than, so x is greater than 3 here, and x is less than 10 here, which is exactly what they told us. I'm not using the or equal to thing because they didn't tell us to do that here. And when I'm reading this, just remember, you read from the variable. So when I'm reading this and I'm saying x is greater than 3, that's the proper way to read it. This is read as x is greater than 3 and x is less than 10. So reading from the variable. Reading this way. Okay. So there's some examples of set builder notation. So let's see, let me get back on track here. Let's move to these special sets, the empty set and the universal set. Cool. From the notes, the empty set is, or the null set, sometimes it's called null, meaning like nothing, is the set that contains no elements. We say that if some set is empty, like if the set A, if we call the set A is empty, we write A is equal to, and then there's the empty set. So the empty set, that symbol looks like a 0 with a line through it, like that. It's like slashing, like not even 0 is in this set. Nothing is in this set. Nothing is in this set. So, here are some questions. Here are some quick little examples. I guess I use red for examples. I'll stick to that. Examples with the empty set. Is 0 an element of the empty set? No. Why? Because nothing is in the empty set. Not even the number 0. Not even the number 0. So the proper way to say this, I could say no. More completely, I could say 0 is not an element of the empty set. This would be true. This is a true statement. So it was false, and now I've made it true. So 0 is not in the empty set. If, let's see, let's say the set A is equal to that, with nothing in there. Is A equal to the empty set? Yes. Because what's in A? Nothing. There is nothing. See? The brackets denote the start and the end of the set, but what's inside? Nothing. So yes, A is the empty set in this case because there is nothing in A. So any set can be empty, or we can rename the empty set, different letters and things like that. This symbol is just used to say, like this set, hey, this set is completely empty. This set is completely empty. Let's look at example 4 from the notes. So I don't know if you figured it out, but I am going to number the notes, or the examples rather, from the notes. And my examples that I'm kind of making up on the fly as I do this lecture, I'll just call them examples. Quick examples versus official examples. And I usually follow my official examples. Roughly, they follow the textbook as well. Sometimes I make changes, though. Determine if the following sets are empty. See, this is interesting. We're getting into some creative ways to possibly write the empty set. So, is this set empty? The set A of negative numbers that are less than 100. Is this set empty? Think about it. It's not empty. Because aren't there negative numbers less than 100? Yeah, -1, -2, -3, -4 halves, -1,000,000, right? There are plenty of negative numbers. All of them are less than 100, right? Because 100 is positive, so of course all of the negative numbers are less than, so no. A is not empty. In fact, A is infinite, right? But we don't need to get into all that. All we need to say is A is not empty. Okay, what about B? The set B of any state that contains the letter Q. I'm going to be specific and say any US state. The letter Q in its name. Think about that. Is there any US state that contains the letter Q in its name? No, right? So what is in B? If B is the set of all states that have this letter Q, that means B is empty. Why? Because there is no US state that has a Q in its name. So B is empty. B is empty. Let's do another one. I'm going to add another example here. Oh, actually, I've written in the notes, using integers or natural numbers and the inequality symbols, construct an example of an empty set. So, for part C, why don't you try to construct an example of an empty set using the natural numbers or the integers and inequality symbols. Or tell you what, I'll do one for set C, or for number C, for example C, and then you can try to construct some on your own. Let's say the set, capital C, of natural numbers, I'll keep it simple, less than 0. Think about that. The set C of natural numbers less than 0. So look back at your notes. The natural numbers are the numbers 1, 2, 3, 4, etc. Which of those are less than 0? None of them. So C is empty. C is empty. And just for further practice using set builder notation, how could I go from this statement to set builder notation? Well, I could say the set of all elements, maybe I'll use the letter N for natural numbers. You can get, creative, whatever you want. N such that, so the set of elements N such that N is in the natural numbers and N is less than 0. Whoops, that's a crazy. That's supposed to be a curly bracket. Okay, that's fine. Even though C is empty, I can still write down what the description was in set builder notation. It doesn't change the fact, though, that C is still empty. So this is a super fancy way of saying nothing, right? The set of all elements N such that N is a natural number and N is less than 0. It's just a fancy way of saying C is empty. C is equal to the empty set. Okay, so you can have some fun trying to construct some empty sets. Let's go on to the universal set. Okay, the universal set. Usually denoted by capital U. Capital U. And from the notes, the definition is the set of all elements being considered for any particular situation. It's called the universal set, and it is denoted by a capital U. U depends on the context of a problem or a situation. Sometimes U could be all the real numbers, or it could be all the natural numbers, or it could be all the people in a room, or it could be all the states. It could be all the states in the United States. It just depends on the context of the problem you're working. So that problem with S, the capital S being the set of states that begin with the letter M. We could take that set S and write it this way. First, we would have to identify what U is. First, we would say first identify U. U is the set of U.S. states. I guess if I wanted to be super specific, I should say the set of names of U.S. states. Not the whole state, not the... What else would it be, though, really, besides the names of the U.S. states? Then we can write, once you've identified U, once you've identified the context of the problem, you could say S, writing in set builder notation now instead of roster notation. So we wrote it in set builder notation back here, M, such that M is the name of a U.S. state that starts with the letter M. Right? Remember that. Still kind of a mouthful, though. But now that I've identified the universal set as being the set of all U.S. states, I could say M, little m, such that M is an element of U. That takes care of the whole M is a name of a U.S. state. And now I'll say M starts with, well, capital M. A little bit of redundancy here because I picked M as the letter to represent the states that start with the letter M. So, once you've identified a universal set, now you know the context of the problem, you can use it in your set builder notation. Sometimes a universal set will just be like a small set of numbers, like 1 through 10 or something like that. Okay. U is just whatever it is defined as. It can be anything. It's universal. Alright. Let's talk about the complement, because complements go hand in hand with universal sets. You can't talk about complement of a set without knowing the universal set going on in the background. So the complement of A, I'm reading from the notes here, the complement of A consists of all the elements in the given universal set that are not in A. The complement of A is denoted by A with a little tick mark by it. So the complement of A is the stuff, so this is read, the complement of A is the stuff that is not in A, but is in the universal set, U. So they complement each other. They have no overlap. For example, oh, wait, real quick, I did write the set builder notation for A complement. By the way, what would the set builder notations look like? It's going to be the set of all elements, A, such that, well, let me not use A, because maybe I would use little a for the elements in the original set A, so let me say, well, just X. X is a nice letter, such that X is in U. So the universe where this set A exists X is in these elements are in that universal set, and X is not in A, the original set. Not in the original set. So if I was to draw a picture of the universe here in a box, this is arbitrary, right? This could be like the set of natural numbers, or it could be the set of all names of people that start with the letter J, or it could be just whatever it is, food items, whatever the objects are in this universal set. And then maybe I've got some set A right here that is some smaller chunk of that data. Like, say, just for a nice example, let's maybe U is all the natural numbers, and A is the numbers like 2 through 10. A complement is the set of all elements that are in U, which is this whole rectangle, and not in A. So all of this stuff in the universal set, but not within that circle of A, that is a complement. Okay, let's look at some concrete examples here. So first I'm going to let U equal Z. So the integers. So -4, all the negative whole numbers, 0, and then all the whole numbers. Well, I guess 0 includes the whole numbers. So there we go. All the integers there. Let U equal the integers. Let B equal, didn't give myself room here. Let's let B equal the set of all elements little b, such that B is an integer. So I could say B is in U. And let's see, let's let B be less than 30. Find B complement. I want to know the stuff that's in the universal set, but not in this set. So this is what this would look like. B complement is going to be the set of all elements, and you pick a different letter. Pick a different letter because you're talking about different elements now. So I'll just say X, such that X is still in that, they're still integers, they still have the same overall home, but I don't want the integers less than 30, I want the exact opposite. Greater than 30, but that's not completely correct. There's one little thing missing. Can you think of it? All of the integers less than 30, that's 29, 28, 27, all the way down to all of the negative numbers. 30 is not in this set, so 30 must be in this set. So B up here is the set of all integers up to 30, but not including 30. So just to write this in roster notation, maybe if it'll help, B is equal to all of these negative numbers, I'll just go down to -3, etc., and then I'll say ... up to 28 and 29, and that's where it stops, right? It's a hard stop at that right side, because these numbers need to be less than 30, so they're not including 30, and then they go on forever this way. Whereas B complements the exact opposite. It picks up at 30, picks up right where this one left off, and goes off to infinity forever. There's no overlap. Alright, let's make a couple other notes and then we'll work example 5, and then that'll be it. A couple other notes about the universal set and the empty set. The complement of the empty set is the universal set, whatever it may be, and vice versa. This means if I take the empty set, complement it, and a little tick mark there, that's going to be equal to the universal set. And that just, whatever the universal set is in a certain situation, if I take the complement of the empty set, I get that universal set. And vice versa, the complement of the universal set that has everything, what's the complement of everything? Well, it's nothing. Okay. In the notes, I called the empty set the null set. Just want to make a note here. Empty set is equal to null set. It doesn't matter. It's just two different names for the same thing. This is a little bit more common in math to use the words null. That's used in a lot of different contexts. Empty set is kind of just used in this context of like set theory. But even set theory people will probably say null set. Null set's probably better. Alright. Example 5 from the text, or from the notes and the text. Let U be the set of 8 planets in our solar system. So, sorry, Pluto. It's a set of 8 planets. Okay. Let A be the set of planets humans inhabit. A is the set of planets that humans inhabit. So can I just go ahead and write that in roster notation because it's only one planet, Earth, right? We don't inhabit any other planet, right? At least not yet. So U is the set of all the planets in our solar system, the 8 planets, and A is the set of planets that we inhabit as humans, and that's just Earth. Find A complement. Well, A complement is going to be all the planets, the 7 planets that are in U but not in A. So, Mercury, Venus, Mars. Can I go in order? Oh, I don't remember them all in order. Jupiter, Uranus, let's see, Pluto, oh, Neptune. Oh gosh, I'm forgetting one. 1, 2, 3, 4, 5, 6. Because there should be 7, right? Because there are 8 total. We're taking 1 out. If A is just 1 element, then the A complement should be 7 elements, because together they should equal to be the same size as the universal set. Which one am I forgetting? Oh god. Mercury, Venus, Neptune? I got Neptune. Oh, this is driving me crazy. It's probably driving you guys crazy too. Let's see. I'm missing one in between Mars and Jupiter. I'm gonna have to Google it. I can't think of it. That's embarrassing. Saturn. Oh, the coolest looking one. Saturn. Oops, Saturn. Cool. Oh, it's between, oh, never mind, these aren't in order. Anyways, Saturn was the one I was missing. Okay. There we go. There's A complement. Okay, you see in the notes I've got some problems marked for review. I recommend going over those problems in the text. They're just extra practice in addition to your Hawks homework, but definitely a good set of problems to go look at to review for the quiz. All right.